ChatGPT, how we came forward. And I believe this is important because whenever I talk to students here, many I feel they have some missing element in the basics. Because I said this and they can connect to that. I believe that would be useful. And I want more interaction. No question is silly question. And I believe I have all the answers. So ask me, drill me all possible ways, and I'll be able to give you answers. Okay. So let's have more discussion and debate, and that would be more useful. So again, we got disconnected. Sorry for that. Will you sustain this, or it will be disconnected during the class?
I hope not. It should show.
So what I will try to cover today. Okay. So I will start from very early 1950s. I believe everybody knows about the Dartmouth meeting, what happened, which is the start of today's AI. Anybody don't know about it? Okay. So great guys like Marvin Minsky and many other researchers at that time, 1956, there was a meeting in Dartmouth College. Okay. And then they proposed a lot of bigger things. Okay. We'll solve machine translation in 2 years. We'll do neural networks and etc. So a lot of promises made. A lot of investment happened. IBM that time, also US government, DARPA, and so on. But nothing happened. So it was the phase of neural network. And they realized that XOR is not happening with the neural network. And then Marvin Minsky write that, his book. And then people started realizing it's not that easy, but it's supposed to be. And then we started deviating. Okay. Then we have linguistics, natural language processing, computer vision, linguistics, psycholinguistics, social. So we started diverging. Whether we are converging now again with the models like ChatGPT, that's an open question. We don't know. But let's quickly look at what happened and what happened in those eras. Okay. So I'll come back here.
You didn't turn on that camera, right? Because you're recording, it will be good for once you put online.
So this is what happened. Okay, in 1950s. So Alan Turing write his, the book. It's not recording.
On.
I can see.
Huh? Can you see color?
Oh, no.
You see?
No.
Why is the battery gone? No, that should not be. Oh, this is not turning on.
Is it not power?
I think we can just go with this camera.
Yeah, I believe that's. Okay. Come back. Okay. So this is the Turing book, and we all know about this, right? And, oh, okay. Visible now? Yeah. So this is the Turing book, and which introduced the idea of Turing test. Okay. And we all know about this. And what happened at the same time, 1954, there was some experiment by the IBM research that time. They made some Russian to English translation with a very handful, Chomsky was a part of this team that time. So they made very, basic translation, and they got so excited. Wow. So we can solve this machine translation problem in 2 more years. So that was a start. Okay. So then, in the successive years, when the Dartmouth experiment failed, people started making chatbots. So chatbot is not new. all there. So Elisa, anybody tried Elisa? Look, so it's so fantastic. I mean, given it has been developed at that era, it's really cool. Okay, and in the code is available. I've gone through it several times, as it's fascinating. Then with the failure of those big investment, etc., AI actually gone down. So basically, the cold era started of AI. If you see the AI history, up and down and up and down. So the first hit point, cold era. So there was bad report. Okay, so we will not be able to do this and so on and so forth. A lot of things being written, and people actually lose interest. So people started doing other things, other fascinating things, distributed system, control system, this and that, and blah blah. So NLP got into town. So then again, certain something started coming in. So core researchers who love language processing, they have been doing. So there are Chomsky believers, there are non-Chomsky believers. So two schools of thought, they have been doing their job. So they have been doing, rule-based translation, rule of, dependency parsing, semantic role labeling. People like Judovsky, Judovsky is not believer of Chomsky. So opposite school of thoughts. So that happened. That have been happening. So one breakthrough happened during the 80s, Bayesian network. So people started applying IP machine learning. So people got, wonderful results. So then, obviously, successive years, support vector machine and all those machine learning started coming in. Then what happened in the, similar, little early, another chatbot came from the MIT, Surutlu. And that is also, a little better than Elisa. And people also got, again, excited, but that excitement remained only for 2 years or so. So now it's a good time we can do NLP. And then, last 2 years and again, gone. And this one we know. The era we are living in from 2000. So the first paper written by the Bengio that we can really use neural network for language modeling. And that kicks everything. So although Mikolov writes the what to make paper sitting in Czech Republic, being a PhD student, nobody supported him that time. And there was a lot of propaganda, negative propaganda. I have listened to them. And this is just timely. Mikolov came out with what to make idea, and Bengio just came out with the neural network-based language modeling idea. So they were not connected at all. So that's got the connection. So people got really excited about neural language modeling and so on, and a lot of started coming. And this we know. And in 90s, although LSTM is actually older, LSTM came a lot ago, but we are still talking about this now. Although people don't talk about it, the RNN era is gone. But this is it. So this is the history. Although we can talk about various smaller pointers, what happened, so on and so forth, but I'm not going to that details. Now, any addition, any comment here?
So I think this is the one stream. There are others like expert system.
Exactly. So that I talked about. So what happened? People who believe that we can't solve AI altogether, people started deviating, started creating different streams. So today I will talk only about the statistical part of the story. Okay. Although I worked heavily with linguists more than 7 years or so, there was a great influence of linguists in the natural language processing. Now it's an open question whether we really need them. I don't take it as a negative, but it's a question. Okay. So people have been trying, one set of people trying to solve language processing with mathematics, only mathematics. Okay. And that came out in various eras. And today, whatever you are seeing, ChatGPT or GPT-3 is actually a journey of last 30 or 40 years. So what are the big things happening in that pathway? I will touch upon that. Although I personally work with linguistics, I personally work with psychologists and so on. I know other areas as well, but I will only talk about the core mathematical thing. Now, beyond this, I want to motivate you. Actually, let me ask you one question. How many of you have seen the PhD movie? None of you? Okay, so I believe every PhD student should watch these two movies, called PhD movie 1 and PhD movie 2. It's developed and shoot by IT. I'll show the trailer a little bit. So it's just beyond NLP so that you get motivated. Just watch.
Listen, being a PhD student, working with a professor, It's a lot like a marriage.
I'm so happy to meet you. Can you tell me about yourself?
Yeah, I was hoping that maybe.
Whole thing typically lasts 5 to 7 years.
Who are you? Oh, I'm a grad student.
Senator and in a bitter divorce.
Yes, I would love to take you as my PhD student. Really? They're kicking me out.
And it all culminates in a big ceremony where you walk down the aisle wearing a fancy gown.
Today's my first day as a teaching assistant for Professor Shu's class. Watched a toast party last night for inspiration. You know that movie doesn't end well. Oh, Captain, but Captain.
Yeah. How's research going? Ask a grad student that question.
Do you have any kids? No. Married? No. Seeing anyone? No. Oh.
How's your thesis going?
Actually, I'm still in school.
Oh. In the highest levels of higher education, there's always someone at the bottom.
Why? Why am I doing this? I have a college degree. A monkey could do this.
Research is torture. I need help with them.
Let's see what you got.
I haven't actually done any of it.
I need your results on my desk by Monday.
What's this number you have here?
That's a 7.
But what does it represent?
The answer?
Actually, sir, I've been having some problems.
But why did you get that answer?
Because the problem asked for it.
In academia, we never use the word problem. Call them challenges, issues, never problems.
Is he supposed to help me?
I have issues.
My
Working hard? You even in this class? I'm hardly working.
You don't feel like you're just an imposter.
Around here? I'll be a grad student forever. I'm going to be 35 in a few months. 35? In phase 7?
President's going great. I'm actually doing an independent study for a professor. It's called Workspace Augmentation of Photon Impingement through Impurities.
I'll higher and deeper.
Oh, I forgot. Some of the students tell you this is late. Could you wait too?
Come on. Can't we just bury them?
Oh, stop feelings.
So if a must watch and should follow the PhD comics over Facebook, you will, definitely find out your thoughts sometimes. That's things you've gone through every day in your research journey. So let us get back to business.
Yeah, this shows me I'm not giving them the right experience.
Okay, get back to business. NLP, natural language processing. Well, let me start from here. Machine doesn't understand language. Simple story. Okay, it only understands numbers. Never understand. So how we can make things machine can understand language? Okay, so that's the whole challenge. Well, this has some weirdness. Okay, so natural language is not natural. Naturally. So there are a lot of problems. So the first problem let me start with is natural language does not follow normal distribution. Everybody understand normal distribution? Okay. If you don't understand, just a quick thing. So these are the things which follow the normal distribution. And there are many. It's just a representative. So normal, natural language does not follow. So this was the 1950s problem. So I don't know how to model natural language because it does not follow my distribution. So I'm lost. Okay. So to give you basics, this is normal distribution. You know about this Galton board? How many of you don't know? I'm simply illustrating what is normal distribution. So this is normal distribution. So as many times you do it, you get the normal distribution. Right? Why? This is inverse from the unit point. Okay. So that's why I'll be teaching. You understand this, right? This is normal distribution. Natural language does not follow normal distribution. Now let us spend little 4 or 5 minutes time to understand normal distribution. Then we'll go to something more mathematical. Well,
Let's begin by talking about pegs. The pegs on my Galton board are arranged in a triangular pattern like this. We start with one peg. Below that peg in the second row, there are two pegs on either side. The third row contains pegs arranged like this, the fourth like this, and so on. Now, it's because of this arrangement of pegs that the Galton board is sometimes called a quincunx. A quincunx is a pattern of 5 objects, a certain way of arranging them, where 4 of the objects are on the corners of the square and the 5th is in the middle. You're probably familiar with the quincunx if you've ever looked at a die. Now, anyway, when the balls fall through the machine, they first reach peg number 1 in the first row. And once they do that, they have a choice. Well, they don't really have a choice, but they will either go left or right. And because of the way the Galton board is designed, there's about a 50-50 chance that any given ball will go to the left or to the right. Once that's happened, they've reached the second row of pegs, where they will either go left or right, left or right. Now, because at each peg, a left or right bounce is equally likely, in the long run, across a large number of trials, we expect balls whose complete paths contain about the same number of left and right turns to be the most common, which means we expect more balls to wind up pretty much right below where they started, and many fewer on the edges, which corresponds to having way more of one kind of bounce than the other. We don't know where any individual ball will wind up, but we can say something about how they will all behave. Now, the actual probability that an individual ball will fall into any one of these slots follows what is called a binomial distribution. But there's a nice thing in mathematics called the central limit theorem, which tells us that under a large number of trials with a large number of objects, like 3,000 balls, a binomial distribution approximates a normal distribution, which is what you see drawn here on board. But this Galton board doesn't just demonstrate the central limit theorem. It's got a bunch of other cool features. For instance, look carefully at the pegs. You'll see a hexagonal tiling with numbers. That is Pascal's triangle.
Oh, no Pascal triangle. Only 2? Okay. Now you understand why normal distribution is normal distribution. What is the math behind it? Now see, this is not new. People have been studying this from the time of Pythagoras. Okay, many centuries. So now the people struggling, mathematicians, have been struggling. I know this is so fundamental. Now I can't model language using it. I don't know what to do. Okay. So now just a basic about Pascal triangle.
Let's begin.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam triangle, and in China, it's Yang-Wei's triangle. To much of the Western world, it's known as Pascal's triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs, and you'll generate the next row. Now do that again and again. Keep going, and you'll wind up with something like this. Though really, Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row, and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, Row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting, all ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art. It's also quite useful, especially when it comes to probability and calculations in the domain of combination.
So you can watch this full video over YouTube. So probably now you understand people have been studying this since centuries, okay? And why normal distribution, Pascal triangle is the best, way to understand it, illustration. Now the problem with the mathematicians of 1950 was they're not able to explain language using their known mathematics. Okay, so they're struggling how they can model it. So these two laws actually came out in 1950s, Gibbs law and Hicks law, and which is Gibbs law is still hold true, and it's really useful even today's language model. How I'll describe that. So let me just first talk about Gibbs law. I think many of you know, but
hey, Vsauce, Michael here. About 6% of everything you say and read and write is the is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to. An is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zipf's law, and it doesn't only apply to English. It also applies to other languages like, well, even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zipf's law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget. There are plenty of theories about why language is zippy, but no firm conclusions. And this video doesn't.
I pause here. We understand Zipf's law now. Okay, and that was a breakthrough in 57 or so. And yeah.
Just reiterating what he said. Till now, we have not found any scientific justification as to why the Zipf's laws follow. It is only empirical.
So the answer, in short, no. So there are theories which try to explain this, but we have no firm conclusion. But we know this is the way it happens. And since we know this, we can better model it.
Yeah, but it's all based on the empirical
right.
Throughout history.
Right.
Without a
and we never find any exception in language that it does not follow Zipf's law. So that's how it is. Question? Comment? No? Okay. So this great finding, there was another one. This is a Zipf's law. I believe everybody knows. So there are two problems. So when we have been, we in a sense, NLP researcher like us, we have been developing rules. Now the question, what should be our dictionary size? What should be the wordnet size? And so on and so forth. So this is a simple law by Habe. It says that your distribution follow this rule. Vocabulary size equal to k into the power beta. What does it mean? We'll come back here. Let's see the graph. Very simple graph. Okay. Let's say you take down whole Wikipedia. You are reading every 1,000 words and you are plotting that in x-axis. And in the y-axis, you are plotting how many new words were encountered. Am I clear? So what will happen to this graph? It will come on. So it will grow like this, very steep initially. After a certain point of time, it will start becoming flat. Right? So typically, if you look at English corpus, news kind of corpus, the convergence comes around 80 to 90K. So after that, whatever you receive is typically name entities. Always will come. You can't create a dictionary ever, which is complete. That's not possible. So you'll keep receiving those new entities. But if you look at biomedical domain, name entity is quite higher. So this curve will be much steeper. And the convergence will come much later. Maybe 150K or 200K. So basically your entropy is higher in that corpus. So what it says, and if you look at other languages, like Indian languages, that convergence comes very late, 200K, because it's more complex. You have more words, you have agglutination and a lot of other things. So complexity increase. So what this rule says, k into the power beta. So beta is typically square root for English. Normal news kind of tone. If you go biomedical, things will be different and so on. So this Zipf's law. Now, how this is helpful? And even for your information, even Google received 20% more new name entities every day. So that is not going to get over ever. Okay? So that's the way language is. You can't make a dictionary which is complete. Right, let me jump this. Okay, so this was really helpful. There are a lot of research on this using Zipf's law to predict the index size. When Google first came, so there's a Murray's law that web size start getting double in 18 months and so on, right? So the question is for Google, what should be my index size for the next year? So if I know this much extra data I'm getting with the Zipf's law distribution and Zipf's law distribution, I can predict how much memory I need. Okay, and that really worked well. If you look at Segaer initial papers, you'll get Zipf's law and Zipf's law everywhere. So people are actually predicting the index size and so on. So here it becomes very useful. Now coming to directly the encoding thing, right? So machine does not understand words, language, not at all. So we have to represent natural language word in some mathematical way so that we can process it, right? So basic thing what we did, one-word encoding. Everybody knows about it, right? So you got a dictionary or a vocabulary. Whether this word present, you put 1, otherwise 0, right? You can also do that for document. Your vocabulary, whatever word appear, you say 1, otherwise 0. What's the challenge with this? Yes. If you want to calculate distance between 2 words, you always get what? Root 2. So basically your vector space distance is meaningless. That's the problem statement for 30 years of researches. So basically you want to create a vector space which is meaningful, not root 2 always. What? We don't know. We'll find that out, but not root 2. Okay. So that's the problem. Now this man come in picture. Okay. And this is the case of father of distributional semantics. So he was a linguist during the British India time. He was a professor in Punjab University in India. And he said this: I can probably model words by looking at their neighborhood. He said that he did not have the technology at that time. Just said it. You know Euler's law? Something like Euler's law. Everyone knows Euler's law? Okay. Okay. So the story is a German medicine practitioner who used to write diary. He wrote, okay, we know a square plus b square equals c square, and we have numbers for that. 3 square plus 4 square equal to 5 square. But we have no, equation we can write a cube plus b cube equal to c cube. And I know why. I don't have space here, not able to write it. And he died. Sorry? No, Euler's law. Okay, I'm coming to that. And he died. He did. I know I don't have space to write here. He died. His grandson auctioned this. Somebody did. Wow, he knows the answer. I don't know. Hey, anybody know in the mathematics community this problem? Nobody knows. And that took 30 years to solve the problem. Puzzle. Why? Okay, why does not happen? So something like that. He just said it. He don't know how to do this. He just said, I can do this. So that man died and this come into picture. Now, we are in 80s, early 80s. So on the one hand, great linguists, they did a lot of great things. They have been developing dictionaries. Typically like word name, top and this and that, lot of linguistic rules, take verb, tense aspect, modality, gender, number, person, this part, case, grammar, lot of things, context-free grammar, we are discussing. Now, another set of people come in and say, hey, you are so limited because you can't understand that, car and, wheel has a connection. That is not there in your grammatical relation. How can I model this? So synonymous, not synonym, started coming in picture. And people were so crazy, how I can model this using mathematics. People don't know how to do this. But the problem statement exists. People started targeting to solve the problem. Am I clear? What's the problem? So one way people are doing grammatical thing, one way people are trying to solve this using mathematics only. So I believe that's the time, concept net, etc. things on. Okay, so now Peter Tunney, who now in NRC, National Research Council, who came out with this PMI idea in the NLP domain. Everybody knows PMI, right? I don't have to explain too much. PMI is simple. So there are pair of words, okay, pair of, or quadgram or trigram and so on, who appear so often. So they have some kind of relation. Credit card, shopping card, and so on and so forth. So can I mathematically understand that this 2 word or this 3 word or 4 word having higher connection mathematically? Model it. So here is the basic formulation. Probability of xy divided by probability of xy. Very simple, right? So people started modeling this. Okay, so here is my fellow letters, fellow citizen, at home, on earth, blah, blah, blah. So this is the frequency of the first word, frequency of the second word. By your frequency, you calculate the body, PMI. Higher PMI is relationship, lower PMI is lower relationship. Now the problem with PMI is it also can become negative. So people say, no, this is not useful. Let us do only positive PMI, PPMI. Okay? People say, no, that is also not good. Let us branch it out. Let us do log. So a lot of things happen. So, but this is the basic theory. Everybody understand here until this point? Any question? You can stop me and ask me any question, okay, anytime. Now, language modeling started coming in picture. So what is language modeling? Simply the fill in the blanks you did in your school days. So if I ask you which one will go, first blank, and which one will go in the second blank? Second one would be? How do you know that? Sorry? Right. So basically the function words. So that gives you the hint. So basically it is telling you if you know the language grammar by looking at the context, you should be able to predict. Right? So how can I capture that grammar in the modeling? Mathematically. Again, whatever I'm talking today, mathematically. I can talk about various other things. I also work, but I don't want to. So how can we learn? I mean, I just skip this. You all know this. Okay. So just a piece of trivia. So how language model is so important and so useful? I believe everybody has a smartphone and you type it, right? So how fast a human being can type on a QWERTY keyboard? You understand QWERTY, right? Not smart keyboard, QWERTY keyboard. So there was a Guinness Book of World Record in this year, 2011. This test has been given to a lot of people. And this man from the US, he typed this whole 264 character in 56.57 seconds with a BlackBerry keyboard, QWERTY keyboard. That's amazing. Okay. But now look at today's smart keyboards. What you use in mobile phone. That gives you this speed. Even a normal human being can achieve this speed. It's so fundamental in communication, whatever you use today. Just a piece of trivia to kind of make you understand how this happens. Have you seen this one? Anybody? How your autocorrect actually make mistakes and how sometimes you got into trouble. So that's a problem with language modeling. Let me just skip this. Now let us jump into basics of language modeling, and then I'll slowly build up on top of this. And I mean, I don't have anything in my mind that I will complete this much. Whatever time permit, we'll do, and we'll jump to next. Okay, so here is the basics of language modeling. So what we are trying to do, we are trying to calculate the probability of a given word sequence. Good. Yeah. So, and if we can do that, how it could be helpful? So people at that time, I mean, the usage of language modeling in any kind of task of NLP is a new thing. Okay, never happened. Earlier, when I did my PhD, there was group. This is a machine translation group. This is a dependency parsing group. This is a sentiment analysis group. And so this is a WordNet group. Okay, now everybody do everything because of language modeling. But the motivation was there. If we can do language modeling better, we can do a lot of things better. Okay, for example, your OCR thing. To write RN, sometimes it might be mistaken as an M. So the machine correct it by looking at the context, right? So a lot of such things. Okay. So how we can do this? So we are trying to calculate the probability of a given sequence, right? So we have to calculate the probability of a given word, WI, given the context. What is the context? I'll talk about that later. Okay, so there are a lot of discussion, debate in the NLP community. What is context? So, but let's say all the previous words is my context for the time. Okay, so I'm trying to calculate probability of WI given all the word from 1 to I-1. So how I can do this? Simple. Count up all those words given a corpus, all the previous word. Let's say I like chocolate. I want to predict given I like, what is the probability of chocolate? So what is the probability of I like? I like chocolate versus I like. So that is my count versus count. Okay, so let's say I'm trying to do this one. Given this sequence, its water is so transparent that I'm trying to predict the next word. What is the next word? Right? So next word could be anything from my vocabulary. What is my vocabulary size? Let's say 60K or 80K. Let's say 80K is my vocabulary size. Now what I have to do? I have to basically do this, right? Count its water is so transparent that the divide by how many times this occurs in my whole corpus, divide by how many times this appears. Its water is so transparent that. I'll do this, right? Mathematically, this is the formula. Now, what is the problem? So language model is giving you a branching factor. That from this branch, how many branch can go? So Raj Reddy's, algorithm comes here. I'll talk about that later. But this is impossible. Why? Because language is so diverse. You can write language in many ways that you might not see the exact frequency of that particular phrase several times. So what you might get, basically zero. That's not going to work. Right? So what happens? Now the man called with the beard, Markov chain comes and takes it. So we know Markov chain. Everybody knows Markov chain. So Markov chain says, okay, now simplify this. You're supposed to do that, but if you break it down to chain rule, you can solve the same problem with simplicity. Okay. So how we can do this? We can break it down to simpler things like this. We say, okay, we are not doing the whole sequence. We are breaking it down. We are saying every time I'm going to print the next word. Okay. What is the problem with that? That is too shallow. So now what is the sweet point? Whole sequence I can't do. Only last word I can't do. So I have to find out a sweet spot which can give me both. So obviously, NLP community again, debated on this for more than decades. So bigram, trigram, quadgram, pentagram, what domain, what problem, and etc. But again, it's an open question. Okay. So here is, if we can simplify this in simplicity. So what is sound? So I can look at two words divided by the first, previous word. So basically, I'm doing bigram. Okay. Applying Markov chain, I am doing bigram. I'm trying to calculate the probability. Are you good here?
Yeah, just one question.
Yeah.
Can you give me a year and the name associated with
Markov?
Not Markov. This is all dating back to Markov?
No. These are.
But the whole notion of statistical language.
This one. This one. Yeah, these are all 80s.
This.
80s.
80s?
80s, yeah. 80s. All 80s. Late 80s and early 90s.
And a name?
Mostly.
Not Markov, obviously.
Yeah. So Martin, Peter Turney, these are the major people at the time. So Martin was a professor in Colorado Boulder. I don't know whether he's.
Really?
Yeah.
Hey, Spanish, catch that?
Yeah.
Boulder.
Yeah. Okay. Now, okay. So just an example. Let's say I have all these sentences and I want to do language model on top of it. So what we learn from, we'll be doing bigram. Right? We'll look at two words and we'll calculate. Okay. So here it is. What I'm doing here, I'm getting matrix. Okay. And I'm trying to capture how many times word appear with each other. Let's say 1 and 2. Okay. How many times they co-appear divided by the frequency of 1. Okay. So what I'm getting, the 2 is very likely after 1. So that's the English language. So it's 0.66 and so on. So if you look at all this, so you can probably see the food is higher probability after Chinese because something of that sort. So 1, 2, eat, and etc. So I'm just just giving basic example. So if you do a very big matrix, let's say 80K is your vocabulary, and you try to do this bigram versus bigram, you'll get this probability. So this is your basics of language model. Although today's language model does not work this way, but just trying to make it. So what we are able to learn here, basic language grammars, 1, 2, food, and so on. Do you know Google Ngram? Everybody knows. It's downloadable. Everybody who don't know?
Ngram will give you and ask how things publish.
So you can search for any bigram, and Google has a very large corpus. They can search and can tell you, kind of distribution over their corpus, and over the years. So would you like to try something here? Anything? Bigram try or anything? Any word?
Table chair.
Sorry?
Table chair.
Table chair. No. Let's a little more complex possibly. Donald Trump, let's say.
No, but that is probably not a very good one, right? Because that is more of a
yeah. So you can see, right? Donald Trump.
Not a long existing.
Yeah. So say something else.
Language model.
Language model. Okay. You can see from 1960s, there are now obviously people are talking about language model everywhere. Okay. Okay, table chair.
Huh. What would that be?
Yeah. Huh?
I'm worried about this. Why are we seeing that increase in table chair? That's starting to make me think.
I don't know. Okay, so this is artificial intelligence, 1960s. There's a spike, then it goes down, and again.
But if this is true, is this percentage wise or?
Yeah, this is the kind of frequency, yes.
So, I mean, because corpus sizes continue to increase. But,
yeah,
That's what I was wondering.
But
they scale it.
But it is interesting that we still not reached the height.
Okay, so what I'm more interested, I can probably show you the. Yeah, hold on. Okay, guys.
I think we should move on.
Yeah, we should move on. But what I want to show, there is a link here. You can actually download this whole and use for your research if you really want to. I wanted to show that. I don't know what it is. Yeah. Yeah, I believe it is downloadable even until 5 grams and for not only English, for maybe more than 200 languages. So you can download and use it for your research, whatever way you want to. So it's open. Okay, let's get back to this. Okay, so this was all late 80s and 90s. People started doing this in all possible ways, all possible n numbers. What is the sweet spot? This language, this domain, this and that, and blah blah, so on. So this was a parallel thing, right? One way NLP, linguistic have been saying, no, we have to learn linguistic rule, dependency rule, connections, and so on. And these people have been busy in doing mathematics. And there was no match, okay? And there was a lot of fight, okay? So then IR community born, there are more magicians, NLP community born, more linguists. Even in top conference, there used to be panel discussion and debate. We are going more linguistic way or more mathematical way. I don't think those exist today, but this was the time. Okay. So now we are talking about language modeling, fantastic. And these are all mathematicians. They have to evaluate, right? Until we evaluate, we don't believe. So how to evaluate? Okay, language modeling technique. So these are the things: intrinsic and extrinsic.
But this language model, the objective was still very limited, right?
Yeah, I'll come there. I'm still talking about 80s and 90s. Obviously, they are trying to.
What they were trying to achieve was still very
limited.
Just like sequence to sequence model and trying to predict next word is that's a very
very basic thing they try to see.
It has a lot of use, but
right. But it has not been seen as use even 5 years back. I mean, with the BERT and GPT, how the whole NLP got changed, it was never thought of or never,
in one sense, it's wonderful that, predicting next word is such an important thing. In another sense, people are losing the sight that this is a very minuscule type of, aspect of all the language understanding or use.
Agreed.
And there's so much more left.
Right. Agreed. So obviously, I mean, that's the way science is, right? We'll start and we'll create another one.
So,
yeah.
If everything started with joint probability of a series of tokens and Zipf's law exists, isn't statistical learning theory out the window? What was the point of even trying it? Because there's.
Okay. I'll exactly come to the next thing. So Zipf's law is very useful here. But let me talk about the evaluation so that you understand how to evaluate, although it exists today, and then I'll connect the dot back with Zipf's law. So that's what I'll do. Okay, so from here, people started talking about two kinds of evaluation. You remember I talked about every distance is root 2, which is not useful. So how I can make vector space more meaningful? Your world model. Okay, so basically the distance between king and queen should be equivalent to nanometer. Ideally, that's something. So intrinsic evaluation, extrinsic evaluation. What is extrinsic evaluation? I'll do language modeling, I'll apply it to my problem. Whatever problem I have, part of speech tagging, sentiment analysis, machine translation, etc. Intrinsic is I will intrinsically see the quality of the modeling. The two-part. So intrinsic perplexity. So let's talk about that. Now keep attention here. It's very important. Okay? So if you look at this fill in the blank tree, and if I ask you which one will go to the first, which one will go to the second, and which one will go to the third, what will be your answers? Second one is direct, but we don't have an option. Okay. First one. First one. Sorry. Pepperoni. Okay. Mushroom. Could be anything. Okay. Second one. At least we know probably, but we can't see the option here. But we know what is the option. Last one. Okay. So what is the notion here? The notion here is the language is so personal. In the first option, you probably have multiple choices to go in. You are not very certain. Mushroom can also go, pepperoni can also go. Chicken can also go, I mean, whatever, right? In the second option, it is very certain. Only that one will go, nothing else. Third one, anything can go. I can see anything, right? And that is not wrong. So now the question is how I can evaluate a language model. Right? So I have to have a gold standard, manually annotated, and then do an etc. But this kind of variability problem is there. Right? So again, all the believer mathematicians say we have to do something only by math. And that took so many years, but they did it in some way. So here is the point. So now the good part is you have a large team. You take out 80% data, say this will change. I'll keep 20% data for my testing. Now, what is the good part of the testing? You already know what is the word is supposed to say there, right? What you can do, you can take the first two words and say, okay, I will predict the third one. You can take the first three words, you can predict the fourth one. And you know what is the output, right? So you will be evaluating your model that way. Okay? Understood? So here it is. So what I'm trying to do? Trying to calculate the probability of a sequence, probability of W1 to Wn. Forget about the root. I'll explain that later. So that is my goal, right? So what will happen? So now I'm trying to do what? In every utterance or every instance, what is the probability distribution? Now let me explain very simply. At every instance, what you will do? What is the vocabulary size? Let's say 80K. So what you will do? You will create a probability of 80K. Simple like softmax, right? So this word 1 is a probability of this much. Word 2 is this much, right? And you say, okay, if I now rank them, word 5 sit here. I rank them, word 3 sit here, right? That is you are going to do, right? Now the question is, how many times 2 or 3 words are very nearby? So their probability might be same. This one can also sit, this one also sit. Now the question is, how certain your system is to give you only one option, not 3 options. I'm not interested in 3 options. I'm interested in 1 option. This is the notion. I want to evaluate my language model based on that capability. Understood? So what I'm doing, I'm averaging out for all the n words, 1 by probability, basically inverse. So given this whole sequence, every instance, what is the confidence of my system? Giving only 1 word. That's it. So how I'm calculating? 1 by probability of the whole sequence. Now I can just rewrite mathematically. It's a summation of 1 by n wi given the whole sequence, right? 1 to I minus 1. Right? I'm calculating the probability of a given word based on the previous context. I can simplify with the Markov chain probability of I given the previous word. I mean, you can write 2 words, 3 words, whatever. So this is your formulation. Is it clear? It's very simple to understand. It's not very complex.
is basically the certainty or the confidence of.
Okay, hold on. This is the mathematics, and now understand the intuition part. Okay, intuition is not mathematically correct. I always give this caution to students when I teach. It's not mathematically correct what I'm going to say now, but it will, ease you to understand. Okay, so if you think perplexity lower is better, what does it mean? If you try to understand very, layman way. So given a sequence, basically your system is giving you 100 words possibility. In this fill in the blanks, 100 words will say. And this model, unigram model, is giving you 1,000 words. You understand the intuition? So given and fill in the blanks, how many words the language model is giving you? Okay, these are possible candidates.
The number.
Using the perplexity. Perplexity.
In the terms of a normal thing like reducing the complexity of the words which are possible in that.
Right.
The lower the number, more certain you are.
Right. The lower the number is certain you are. Okay, and that's why it's called perplexity. How perplex your system, or how certain your system. Okay. So what should happen if you have a very good language model? Perplexity should be very low, close to 1. Ideal. Am I clear enough? Everybody understood what I said?
There is no upper bound.
The upper bound is 1.
For perfect.
Upper bound, it could be anything. Okay, so I had a paper on code mixing thing. Okay, so if you think about full language when mix up, heaps will actually jump like this. Okay, and believe me, we had around 1 billion corpus. We never reached the convergence, because social media text, you have a lot of word plays, conventional, non-grammatical writing, words are different. Even Akhe, the eyes in the Indian language, you have 20 variations, right? So we never reach the convergence. Okay. So if you never reach the convergence, you will never reach the perplexity in 1 number. So our perplexity was 4,000. Open challenge.
Is the leverage here the language model or the structure in the corpus that's
both
applying the language model to?
Both. Because see, if you try to see Hibbs law in Twitter, it might go even in 400K. You will get the convergence typically. So basically, it says you need a lot more data to do the same thing in Twitter, because your data is so very, the entropy is so high, you can't model it using only on a small amount of data.
But shouldn't there be something in the structure of the data that
Absolutely
corresponds to the structure of the world? I mean, there are certain things that you're just not going to say. You're not going to talk about these days, or versus. I mean, depends on your notion of the environment, but there's certain things that shouldn't happen. Not because it has anything to do with the language model, but because it has something to do with the structure of the world.
Exactly. Absolutely agree. Because see, perplexity is a number dependent on your context, right? You are predicting a word based on looking at the context. Now, if you get a data set where you have a lot of words which are only seen one time or probably never seen, then your model will never be able to do anything. It will be basically giving you zeros or close to zeros. Basically, it will not learn. That's it. Yeah. So she can.
So we measure the complexity of the entire corpus.
Right.
Okay. And does it have a mathematical relation with the Heath's law convergence?
Absolutely, yes. So these are connected. I mean, I'm quite sure there are papers, but here it is. So you think you have a very complex data set. Okay, as I said, Twitter. Now compare wiki and Twitter. So what is happening? Britney Spears has 30 variation in social media. I mean, we say. So, or Shakespeare, 40 variations. The name, because people don't know how to write it. Okay, so if you take such a corpus, obviously what variation is going on, your convergence will come much later. So when you are modeling language in terms of mathematical modeling, you need a lot more data to reach out that level of perplexity. Yeah, so obviously Hibbs law and perplexity have a connection. Simple direct connection. More question here? I'll
So perplexity is a good language.
Yes. So if you look at today's, okay, If you look at GPT word and today's language model, they're in the range of 10, 15. So that's the way we have reached.
10, 15.
Yeah, 10 and 15. So that's the range. I don't think we'll be able to go down to this because that's not possible, in a large data set and etc. So ideally one should be, but one cannot be possible either. So 10, 15 is a huge number, huge, benefit you have.
That's just some kind of generic corpus. I mean, it doesn't.
Okay, so
doesn't the corpus matter here?
Yeah, absolutely corpus. So people typically do it on Google Gutenberg corpus, which is very big. BNC corpus, British National Corpus, that's a big one. Paintry Bank, which is also a big one. So these are, typical, very standard corpus NLP community have been using for, more than 2 or 3 decades.
But shouldn't I be able to get complexity down if I work in, I don't know, biochemistry or something? And I just look at biochemistry.
Absolutely. If you go to biochemistry or biodomain, then, as I said, the major problem is you get a lot of new entities whose frequency is very less. So your Higgs law will go up like this. So definitely you need more data points to, converge. Absolutely, that's true.
This is beside the point, but in the morning paper, all the perplexities were in the 10, 15 range and it was all classified as human. But you're saying that should be modeled.
That is today's model. Even if you see the Megha's paper, when, so GPT-0 is saying that if the perplexity is too low, that means an indication is a human intelligence. That's the assumption. Okay. See, GPT-0 came last week after ChatGPT. So that's the kind of discussion people are doing. Now, can I look at sentence-wise perplexity? Okay, so earlier sentence was so grammatically correct. Now you write wrong sentence. So all sort of things people are discussing. But so if you want to see, let's see. So if you have a question, come on. So let's say pick up one.
Do you guys have the other class today?
Oh my gosh.
Okay. They have to go to the other class.
Yeah, so you tell me when I need to stop.
I think now.
Okay. Let me just show this and I'll stop. Yeah, so if you go here. So, okay, so see, these are the perplexity, right? In today's language model, 10, 11, 12, 15, 16, 17. This is the leaderboard, yeah. So we are in the range of this one. Okay. So anything else you have in mind? Ask me, otherwise we'll close today. Oh, good. Anything, Sabana, online?
I'm good.
Sorry? Oh, yeah.
That is just
Okay.
Okay, no. I have in each slide, I have it. So I still did not reach out, give anything out, but I'm just
like all these research papers.
Yeah. So I will point out, read this one, and I will point out, not only listen to me, listen for this part, listen to this guy who probably did better job than me. And so I have all these things in my slide.
Did you share the presentation?
I will.
So I would like the name of the person who you credit starting the language model stuff. You said it came out of Boulder. That's very interesting to me because that's where a lot of the psycholinguistics work came out, including like semantic analysis. So I'd like that. And then the other point that I would make is not every language is word-based. And we are definitely eliminating those from our.
So you're probably, I got you. So you're probably, let me answer.
Pardon me?
Like African
languages. African languages, Arabic languages.
Okay. So that's a German. Okay. It has no derivation. Okay. Or Africa sometimes no derivation. And Chinese has tonal language. So one word means something. So in those languages, there are a lot of work on delimiting words.
Yes.
That's
basically the problem.
Yeah. And the tonal language has a problem. It's a kind of more or less like a W. But you can't solve that using only written language. You need speech for that.
Yeah, but the languages that I'm worried about right now would be the Arabic languages that basically compress words and syntax into the same token. Basically, that's the problem. And then unpacking, then the little inflections, the little changes on the word are dependent upon other segments in that word. So that is a much harder problem.
Yeah,
we ought to be worried about that. We're eliminating a big portion of the population in our language analysis.
I'm the little baffled by the fact that even though there has been research on this for such a long time, we have still not been able to find a scientific justification as to why this law and why not normal distribution.
Yeah, so if that intrigues you can start looking towards that. That would be interesting.
Solve that.
Yeah.
No, I don't think these people say like why that is what is bothering me. Why have we not been able to find a justification?
So this year's AAA Knowledge Augmented workshop papers, if you see, there's a paper on how zip law affects distributional certificates.
That's the topic I will start in the next class. I stopped there actually. Okay, so just to, whoever wants to go for class, they can go. So this is the way I'll go. I will talk about the GIPS law, how we do this. Then I'll jump to a little bit of IR, what IR community did, fantastic. Then again, I'll come back to the statistical thing, what to pick. I'll teach you what to pick. And then I'll go to CLO, and then I'll talk about the evaluation. Then I'll go to neural language model, I'll go to transformer, and then I'll end. So that's the kind of journey I have. Savannah, any question from your side? Or we can close?
No, I'm good. Thanks.
Thank you. Bye-bye.
Thank you.